last time we had a look at the security problems, and also we had a look at BitTorrent. And maybe we should once again go through BitTorrent to make it all very clear how it was working. One moment. Yes, that one. Because it's really too popular to be unnoticed, and I just want to go through this exercise again. So what you have to keep in mind that you have only a few elements. So you have on one side, if you want to start the whole, if you want to offer a file, what do you have to do? So you first use a small tool which creates out of your file, for your file, a torrent file. It contains the file name, it contains how many chunks you have chosen, because you can also differentiate the chunk size. Then for each of these chunks there's a hash, so once people download it they can check whether it was verified. And also you tell which tracker you want to use. You can also use different trackers. And the tracker then contains the information about who is participating in the swarm for this single file. So that was the other point. So there's only one single file, so each swarm is just for one single file. And the swarm, this is a set of nodes which want to share it, which either have it completely, these are the seeders, or which have it only partially, these are the leechers. So you get the list. So you contact the tracker and tell, I want to participate, and the tracker gives you a peer list of roughly 50 nodes. Okay, out of these 50 nodes, you cannot ask them to, you cannot contact them just by your own, so you have to wait until they select you in their own unchoking mechanism. So that's the thing how everything starts. So you can only have 4 contact partners, so this is the share set with which you really exchange files. And if you don't have any chunks to share with, then you cannot pick any node. So they have to select you for their share set. And how is it done? This is done by every 30 seconds, the slowest in their share set is dropped out, and they randomly pick out of the peer set of this peer list of 50 nodes, one randomly. And by this you get your first chunk. So somebody will pick you and you are happy and you get your first chunk, and maybe somebody else picks you, and in this 30 seconds you get a few chunks. Then he will notice this guy didn't give me anything, so he will kick you out. But you can already start with this few chunks that you have to select yourself some peers from the peer set. So you can select those and for your share set, for the few peers, and give them your chunks. Yes, yeah. And if you upload it quickly, then you will remain in their share set and you will get more chunks by them. So this is how it gets all started. And so while you are having chunks, the tit for tat policy is used. That means, as I said, the share set of the 4 peers is always evaluated every 30 seconds. The slowest one is kicked out. So you have to give a lot in order to remain in the good company of the strong peers. And if you don't give anything, then you are the slowest one, and you will be probably kicked out. So that's tit for tat. And once you have almost all of the chunks, it is very unlikely that you select somehow randomly that node which has the chunks that you want to have. So you can ask the whole peer list, 50 nodes, please, who has this single few chunks that I want to have, and they can give it to you. Okay. And all the time you can also update, and you also update what kind of status you have, so that new peers that are joining also are knowing what kind of offerings you have. And these chunks that you also share with your contact partners, so in the share set of the 4 peers, to always identify which is the rarest chunk, so which is the least available in the whole peer list, in order to share that one with higher priority. So to keep all of the chunks in the network. Okay, so far for BitTorrent. That was the main idea, and also how it still works. And now today, where we want to jump to is is to talk about storage elements. But before talking about it, I just wanted to activate you again once more. So there are some exercises somehow left behind, and it's a good opportunity to become active again. So the question is just to pick up Bloom filters, because they are also relevant. I think not in this lecture, but the next one. So just to pick it up again. So small exercise. We have a Bloom filter given of size m and k hash functions, and now we want to. Okay, I first start with this one. So we have this given. So with the array size of m equals 5 and 2 hash functions, and these are the 2 hash functions. And now we want to add the number 9 and the number 11. So you can discuss it for 1 or 2 minutes. Hopefully it doesn't need more, and then we can see how to fill it. Okay? So what does it mean if we have array size of n? So we have 5 possible elements, and they are, what should I write in for the begin? So this is before inserting anything, so the begin. Then we insert the 9, and then we insert the 11. So what should I write in the begin into these array fields? Any suggestion?
First, I would fill with zeros.
Yes. Okay. Okay, now we want to insert the number 9. So what should I write in the second line? Any suggestions? So what should I write here? Ah, okay. Yeah. Yeah, 0. Yeah. Yeah, that's true, because 1 of 9 is 4. So 9 mod 5 is 4, and 2 of 9 is 21 mod 5, and that's 1. Okay, good. So this is 0, and so these are the indexes 0, 1, 2, 3, 4. Okay. For the third line, what should I write there? Okay. Yes. Okay, exactly, yes. So what we have is we cannot change the 1s to 0. And for 11, the first hash is 1, and the second is genau. 0? Dann ist es falsch, ja. Moment. Ja. That's true, ja. Okay. Okay. Better? Okay, good. Good. Yes, okay. So we inserted it, and we keep the ones, and we just add new ones. So ideally, in order to not have too much redundancy, so this hash maps, so this hash arrays are quite large, so at least 160 bits, that would be good. And now we want to check the membership of 15 and 16. So what kind of information do we get? Yeah, 15 and 16. Okay, yes, 15 and 16. So, any suggestions? Yeah? Sorry? Let's see. So, what do we have to do to find it out? Yes, and that's 0, okay. So we check, that's not one moment. 3, yeah. Okay. So we check then, is here 1? Yes. Is here 1? No. So the result will be that 15 is not member of the set. Okay. And for 16, sorry? 1, yes. Is it in the set? Maybe. So we don't have a no, so this is a false positive, or a maybe. It's then not a false positive, but a maybe. A wrong maybe. Okay, good. That was good to activate. And now we somehow go over to something totally different. So we will use Bloom filters, of course, later on in lecture, but not currently. So just keep yourself reminded that how BitTorrent was working. So you have this tracker, you have the chunk selection based on the rarest first, so that you really try to keep the network populated with all the chunks, so no chunks should be missing. And now one typical application is P2P live and video on demand streaming. What is live streaming and what is video on demand streaming? So live streaming is when the video stream that you want to watch is currently inserted into the network. So you cannot fast forward, you just can try to be at the specific current playback time currently. So that's what is inserted, that you want to have it as quickly as possible. And video on demand means that the whole video stream is already recorded and you can select from different parts in the file also in the future. Okay, so what is it? Why is it relevant? So first of all, because it's very popular. So streaming we had already seen, I think last time, yeah, also when we looked at the BitTorrent traffic that BitTorrent is populating in the upload bandwidth. But the other competitors in the bandwidth usage in the USA was Netflix and YouTube and I think a third one, also with video streaming functionality. So video streaming is now really very popular. And there are also some peer-to-peer solutions like PP Live, which is very popular in China. And Zatu was once proposed by the founders of Kazaa and Skype, so the same people who also had this application for peer-to-peer video streaming. And there are typically two approaches how you can, typically big classes of solutions, how you can video stream. The one is that you have a tree-based overlay, and the second one a mesh-based overlay, where you don't have a specific structure how the peers are connected. So in a mesh, you have somehow, if you look at it, a very random graph where each node might be connected to any other node. In the tree structure, of course, that's very structured, and you have this, you have the circulars, and so they have both their strengths and weaknesses. So we will have a look at it. A little bit about the background also. Other applications, so there have been also tests from BBC to use it as a video streaming, so they also tested it with a small part of English customers, and that was very popular. There are some companies offering that kind of services to support video streaming with peer-to-peer support. And the idea is, if you could do it like YouTube with all the servers to serve all the users with the video content, or you could try to also reuse the upload capacity of the nodes of the peers to save traffic costs. Also, there has been in the Eurovision Song Contest 2006, and also in the years later, the tests to video stream, so to stream the show also with peer-to-peer applications, and there are some measurements how much traffic you can actually save. So if you want to save bandwidth, this is some way to go to really use also the upload capacities of the nodes. This is how Saturio looked like. I'm not sure whether it still looks like, but it was very popular nowadays. So yeah, nowadays I think Satu is not anymore peer-to-peer. So that was also shown in the first slide, because the problem is so you can save traffic, that's true, but you also introduce some issues about security. So what if the malicious nodes try to compromise the stream and to modify there something? So it's also difficult to handle from the software engineering point of view. Okay, so let's come to the overview on the typical solution. So this is one approach, very general. So this is standing for different solutions. So to have a tree-based approach, where there's the initial seeder, the initial server, which introduces the content, and then you try to set up such a tree structure where every hierarchical level sends the stream level one level down, and you have this propagation of the chunks of the files from top to bottom, and the tree size is logarithmic, and of course you try to optimize this tree structure in a way that the more powerful peers are at the top of the network. It's very efficient in terms of you really can take control how many child nodes every node has, and you can really, for all of these powerful peers, find very suitable positions in the trees. So the very weak peers are mostly down in the lowest part, and you can put the stronger peers up and really use their full potential. Also, delay is quite low because you have this logarithmic tree height. On the other side, as you can also see, half of the nodes, the weakest ones, do not upload any content. So this is one point. So the imbalance in the traffic and in the workload that the nodes offer to the network, that's quite big. So the top peers are really doing quite a lot of effort, and the lowest one don't participate in the sharing of the files at all. Also, you have the problem if there's some churn and some peers go offline, then you really have to recalculate tree assignments and rebalance the tree maybe. Some approach to overcome it to have parallel trees, so that you don't have just one single tree, but you have several trees, and you try to push the chunks or the different parts of the video stream over these various trees. So to balance the load a little bit more, then also the weakest peers might be active in some other trees. And also, if one tree fails, you could compensate it over the other trees. But it's a little bit complicated, and you have always the risk that this tree structure is imbalanced, that it's that we have churn. So maintaining the structure of this optimized tree is also time-consuming. It requires also on the fly reassignments, and that makes it difficult to have this optimized structure. On the other side, we can have this mesh-based video streaming, where you could think of like in BitTorrent, where every node is connected to a set of other nodes, There are also circles, of course, and the nodes can actively ask those nodes they are connected to give them some part of the video stream. So it's really very like BitTorrent. So also if you think of the elements of Tracker and Cedar and Leecher, you could think the same, just that you have the specific requirements. So this in case of video on demand and also live streaming, that we have a clear order in which we want to have the chunks. So if we want to start a video stream, of course we should start with the first chunks and not with the last. And every node can select which chunks he wants to have. We will come to a more detailed explanation to it. Oh yeah, maybe then go to the detail and then we jump back to the pros and cons. So here again you have the different peers which are somehow connected to each other. They have this buffer stream, and at this point this is the playback point. So they have to aim at filling their buffer, so their playback buffer, before so always the next time element in the video stream should be filled in order to not have a pause in the display of the movie. And yeah, the blue ones is the available chunks. So if you chunk the file, and the white one is still missing. And also here you can exchange your information about which chunks you have and which chunks you offer with your peers, with the other nodes in this form, and to identify from whom you can download the next chunk that you are missing. What are the benefits and drawbacks? Here it is anyway considered that you change your contact partners over time, so it doesn't make a big difference if one of them fails. So churn is not that big issue for the whole network. So only for the few to which this single node is connected to, but as they are anyway connected to different other nodes, that's all okay. Also, peers can also support, so fully bring in their upload capacities and download capacities, so they really then match with the stronger peers automatically, so that happens. What might be the problem is that the transfer of the chunks and of the playback stream is not that efficient. So you might have missing one specific chunk that is very required for you, but maybe you don't find the one that is having it. And also by trying out different contact partners, you also might end up with some which are slow, and that over an average leads to a lower efficiency and lower transmission speed than the tree structure, which can be really optimized. And you have also this additional overhead. Buffer maps have to be exchanged. You have to check about which other nodes you know and whom you can select. So it's a little bit more inefficient, it's slower, but more resilient to churn. Okay, so how is the chunk selection then done? So what are simple solutions there? So first of all, you could, it doesn't make sense to use the rarest first here, because we want to, our highest priority is to make sure that the playback is continuous, so that you always have the chunk that is to be played next. So if this is your violet playback window, then you have a high priority interval for the next chunks, and this is your main goal to fill, so that for the next 1 minute, I think, you have a filled video stream. And later on, all other chunks have lower priority. So what you again can do here is to have parallel download from multiple peers, because it's chunk based. You can also, like in BitTorrent, connect to the stronger peers to keep all peers busy, to match them with their matching share set. And yeah, for these priorities, so here, if you have these two priority sets, then as I said, we want to really first fill the playback buffer that is going to be played next. And for the other ones, there you can have different strategies. You can also apply the rarest first, and it doesn't really matter which one you select from the low priority queue. Okay, these are the big main concepts in video streaming. There are, of course, different solutions in these big fields. I don't want to go too much in detail because that they are not, so from the big perspective, they are both fitting in these two parts, but in the detail, they're of course a little bit different, which for our sense is not too relevant. So if you know these big two topics and this playback buffer and the priority sets, then that's good. But what I want to highlight is what happens if you have different nodes of different quality. So they have different capacities, and also in BitTorrent, if you have differently strong peers, we might have very weak peers, which are not interesting for any node to contact to. So because they have a very low upload bandwidth, and in the tree structure that we had, they are still served. So the nodes down here, they still get their share and they can watch the video. But in the BitTorrent type of exchange, they might be identified as very uninteresting, so they are slow, and they might get then and when some chunks. But all in all, they get too few to have their playback continuously running. And another point is, so how you can make it even more severe, this problem, is if you think of different qualities of the video. So if you have a very large scale, high resolution video, then you might have the problem that even for playing the first 100 megabytes, for first 1 minute, you need too much bandwidth that the weak peers even can download. So what do we do with them? So do we leave them out? No, there's an approach for adaptive video streaming that I want to present. Again, a little bit motivation. Okay, there's lots of video traffic going on. This is the red. I should have put this maybe on the first slide. So from the estimations, so really video streaming, so not peer-to-peer, but video streaming as such, is dominating. So the share of peer-to-peer net file sharing is still there with this dashed presentation, but video streaming is getting more and more important. And as it was said, we might have different types of nodes, different screen resolutions. So we would like to really fit the video stream also to the weaker peers, because the weaker peers might not be able to download the full resolution video, but they would be able to download a smaller resolution video, but there's probably no offering. So what can be done? That's a big question. Okay, scalable video coding is the goal. So in what is adaptive video coding, what is scalable video coding? So if you think about video coding and video streaming, we always have to ask us with which peers do we want to exchange chunks? So how can we introduce the peer capacities in this? How can we coordinate who is giving which chunk? So the first question is about to which peers do I want to connect to? The second question is, out of these set of peers I connect to, whom do I want to give a chunk? The next question is, if I want to give a chunk, which chunk should I give or ask for? What do I do with nodes having different and changing bandwidth? So even one node might not be always weak, but might be later on strong, and then again get weak again because he's in the meanwhile or in parallel downloading something, and during that download phase in other applications, so his bandwidth goes down, then he becomes weak, and later on he gets strong. So how do I consider the quality of the peer, and also how do I identify these quality changes? So these are some main questions to solve, and especially if we want to make it adaptive. And what is adaptive video streaming? So the idea is to really support different qualities of a video, so that we don't have only one video stream that the peers share, but the peers should be able to share different levels of quality for the same video stream. It's a little bit abstract, so what can you think about? So there are some video codecs like this H.264 advanced video coding, which allow to have some layered video stream or layered data structure which contains, where you can modularly build the quality of your video stream. So I tried to create a graphic for it, but it's a little bit difficult. So you just think about it, you have a base layer, a base quality in terms of resolution and compression and signal to noise ratio, so that you really have a base minimum quality. And if you download more packets to it, more information you have about it, the better the quality gets. So if you have the base packet, then you have the minimum quality. If you select for the same time frame a second packet, a second module, let's say, then the resolution gets bigger or the compression gets better. And we could use this kind of video streaming codec, of this video codec, to match it to the video streaming. How can we think of it? This is another presentation how the video streaming codec looks like. So you have your base layer, and you have this different kind of different kind of quality modules that you can take into. So let's say to this x-axis there's a temporal resolution. So you could have the base layer with 10 frames per second. And if you take a second block, so this tier 1, then you would get 20 seconds or 24 frames per second. So you can improve the temporals or the frames per second. If you go for the other dimension, the spatial resolution, this is how the picture size, so the frame size improves. So in the first you might have a standard definition quality, so I don't know. And if you take one more block, then you might have high definition or 1080i or so. So you increase the resolution of the picture. And the last point is you can also improve the compression quality of the picture. And now the question is, so this block you can consider for one chunk, which is representing a short time frame in a video. So let's say 1 second, 2 seconds. And the question now is, if I start downloading the stream, now during the time I can identify what kind of bandwidth I have, and then according to it I can select the different number of packets I want to download in order to get the best possible quality matching to my current bandwidth. So the very weak peers, they can participate, they just get the weakest and the smallest base layer, and the strongest peers can also participate and they can download all of the blocks and everyone is happy. These are the representations of the different quality levels, so either temporal, so frames per second, or you improve the resolution, or you improve the compression rate. So this is where you can really make a difference. And just to come back to this again, so previously we had the video split into chunks, where each chunk represented a given time in the video, so 1 second, 2 seconds. And now each chunk, that's to remember, is split into these kind of different blocks. It makes it a little bit more difficult to decide at every point in time when you exchange your packets and your data, not just which chunk you want to download, but also which blocks in that chunk you want to download. But of course it's doable. Okay, 1 moment. Okay, so that's a big question. So we want to decide for each chunk, for each time frame, which blocks we want to download. And when can we decide this? So first of all, we can decide this initially. So with an initial adaptation, when you start your streaming process. So that might be if you have a 10-minute long video, then you decide it in the beginning, I have this current resolution, and I take this quality that I want to download. Or you make it during the streaming, so that every few seconds or I don't know, every half minute you check what's my current status, should I switch the quality level. So this is the initial adaptation and the progressive adaptation. And how does it work? So first of all, anyway, you have this initial adaptation that you first decide in the beginning, okay, I would like to start with this quality. Then you select first which chunks you want to have, and of course, your priority is still to have your streaming buffer filled. So you always want to have the next chunk that is going to be played. But for these chunks, you still want to have equally. So the quality should always be the best what you could get for the bandwidth that you have, under the requirement that still you get every chunk that you want to have. Okay, and then you stream, and this progressive quality adaptation allows you to reconsider which quality level you want to choose. Okay, so I could go into detail how you. Ah, yeah, okay. So that's what's basically outset is first you can decide your resolution, then the frames per second, and then how the compression is considered, and there you can, for the initial adaptation, you can consider the resolution, the bandwidth, and processing power that you have, and also during the this is the one that first is considered. So first you check if I cannot have more than specific resolution, then I don't have to go for a bigger quality. And if my current bandwidth is that specific, then I can also identify how much I can maximum go for. And later on with this progressive, then you can really check how the performance of the up to now streaming was, whether there was some, how your experiences with the chunks, whether you are able to fill your chunk buffer. If not, then you can switch down the quality level to improve the probability that you get your chunks that you want to have, so you can react then. So there you don't anymore check your resolution, but more the availability, the throughput, so how much you get and how well it's working. Okay. Yeah, this is basically, okay, yeah, so it's saying, so what you also have to consider, yeah, this is what is available. So if you identify that for the highest quality there are not enough providers, so it will be very difficult to fill my quality blocks of the highest level, then you can ignore it, so then you should not go for it. So this is the really highest supported scalable vector coding layer that is offered by your neighborhood, by the nodes that you know. And the next one is to see how the throughput is for the high priority set, so to really identify whether the chunks that you received, whether the chunks that you want to have to fill your high priority set in order to have the continuous playback is really filled, or whether you have problems in filling it because of you have chosen too high quality level. Okay, and then you can switch back, and then you optimize more for the continuous playing than for the higher quality. Okay, how is it done? Again, very similarly to BitTorrent, but it just introduces the concept of these chunks and blocks. So you still have a tracker which manages the active peers and has the information about who has which chunks and which blocks or which quality layers they are. Then they advertise, so the peers exchange which chunks they have and also which blocks they have in these chunks, so that you can identify which quality layers, which quality blocks are available, and so you can make your selection which chunks to download and in which quality. And of course, also like in BitTorrent, with the process of having the share set of the four peers, which have this tit-for-tat policy. So I try to keep the 3 fastest out of the 4. It leads to the effect that the strongest peers, they cluster. So the peers cluster according to their capacities. Because that's the balance. So if you would have a too strong imbalance, so there's a powerful peer and a weak peer, then the strong peer would kick out the weak peer out of his share set. So at the end it will lead to a balancing where the strong peers are connected to the strong peers and the weak peers to the weak peers. And of course there's also a little bit sometimes an imbalance where the strong peers can give on their blocks to the weaker ones, but at the end we have a common set of blocks which everybody can use, but the network leads to a state where really the strong ones serve each other and can have a look at the high quality, so highest quality layers, and the weak peers or the middle peers they cluster and have the middle quality, and the weak peers have the middle quality. But all of them, and everybody is served up to his own maximum. So which is more beneficial. If you look at how this can be evaluated, so this is there are 2 slides more on this topic. The one relevant part is the relative delay. So if we take the whole playback time, so how long is the full video, and if we calculate the initial delay, so from when on the movie or the video starts, so the initial waiting time and every pausing time that was due to missing chunks. So this is the overall waiting time that you had during the full playback. Then you can see how much in relation to the whole video it is. And the second is the video quality, where you can just calculate the different quality layers and to see what is the best that we can get. And also what is experienced that users don't like if the quality jumps around. So they like to keep the quality, even if it's a bad quality for a longer time, then jumping to good quality and then back again. And I like more to show this one. So here we have the different qualities, different nodes. And it is to be observed how the waiting time is, how it's reacting to the different quality nodes. So here we have only the, here we have this progressive quality adaptation. So every 5 seconds, every 5 seconds on the left and every 30 seconds on the right. And the darker the quality, the darker the color, the higher the quality. And you see, you can either have lots of jumps or fewer jumps, but what you also see is that the peers find their ideal quality level, and also the weak peers can be served, and also the strong peers can be served. And the benefit is really that we have this support for very different kind of peer qualities, which operate on the same data. So with original BitTorrent, this would not be doable, because there we would have one single file and either the weak peers are out, because so we have to decide if with original BitTorrent and this video streaming based on BitTorrent which quality we want to have, and all other nodes below are dropped out, and all other nodes above, which could have more, they are not fully satisfied. Okay. Good. Any questions to this video streaming? So what we had seen is basically the 2 big, some big quality, 2 big solution categories, like the tree-based solutions and mesh-based solutions. And mesh-based solutions, like using a modified BitTorrent, which only differentiates in the chunk selection, so to not optimize for rarest first, but for the playback buffer, so that you have this priority set. And then we had seen this quality adaptation option to support different qualities of users. If not, then I would like to activate you again to see what you had. So I think three lectures ago, I think Andreas was introducing the clustering coefficient. Is that true? Anyone knows what the clustering coefficient is? So if I was looking at the lowest line, I think that you have already seen. Oh. Gut, super, sehr gut. So then the question would be just to reactivate that knowledge and to see what the clustering coefficient of the nodes 3, 9, and 12 is. So take your time, 2-3 minutes, and then we can discuss the results. So, any suggestions for node 3? One? So, node 3, no. So, it's not one. One is rarely the 3. So, in any test, it will never be, rarely be 1. So, never. Okay. So, what do we have? So, what is the clustering coefficient? It's written there. Number of links between the vertices of the nodes within the neighborhood of the node 3. So how many nodes, how many neighboring nodes does node 3 have?
3, aber ich glaube, Potenzial ist ein Drittel, oder?
Ich glaube ja.
4,17 kommt daraus, also ungefähr.
Moment. Let's go through it. So, okay. So how many links do we have between the nodes of the neighbors? I mean, there's, so how many, so I just want to build it up. So how many nodes, to how many nodes is node 3 connected? 4. Okay, that's good. So how many possible links can they be between 4 nodes? sense. It's very likely that clustering coefficient is always easy to ask in exams. So, and it's also relevant for 12. Any suggestion? Yeah. Okay. Light frequency. Okay, we have 6 neighbors. Good, yeah. Okay, so why does it tell me how you get the number of links? Okay, okay. So first we calculate how do we get the number of links. Okay, let's make it for the node 12. So this is node 12, and he has 1, 2, 3, 4, 5, 6 neighbors, and the possible number of links between the 6 neighbors is always 6 times 5 divided by 2, because we consider only bidirectional links. So that's why we have to divide it by 2. So it's always k times k minus 1 divided by 2. And then we calculate, okay, how many links are there between them? This is the 1, this is 2, and this is 3. So that's why here comes 3. Triangles. So we look at the links between the neighbors of. Yes, you can see it that way. Yes, 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 yes. Okay. Yeah. Okay. Good. Okay, why is this relevant? Also, clustering coefficient. So the point is that overlays with, I think that was also motivated when it was introduced, that the more, how to say it? Okay, so on the one side, if it's too clustered, so if the clustering coefficient is too high, because all of your neighbors are connected to themselves, then typically the diameter of the network is very big, because there you have to really go. I think there was this nice graphic. So the higher the clustering coefficient, the more connected the neighbors around them are, the less connections to the outside they have, and the longer your routes are. So this is on the one side. On the one side, it should not be high, but if it's high, then that means that. Okay, just to give you another example, now I know how to present it better. So especially if you look at chord. So in chord, all of the nodes in their neighborhood, because of the first fingers, are very connected. So every node is connected to its predecessor and to its successor, and also the successor is connected to its predecessor. So within your small neighborhood in the routing ID space, so you know many nodes in the small area around you in order to have a good routing at the end and have a few outgoing links, which lead to this jumps to the closer position. So if you would have a small clustering coefficient, that would mean that you have not so much knowledge about your surrounding and that your routing is more difficult to terminate. So you need a specific higher amount of clusteredness in order to have a finalized correct routing at the end, and that you can also have several parts for the final steps. And you need also a few steps jumping around so that you can really have this logarithmic routing. This is the rough idea, so that higher clustered networks are beneficial for routing. Okay. Coming to the second point that I want to talk about today is about storage systems. So what are storage systems? Because up to now, we had only DHTs, so distributed hash tables, and of course we had also unstructured networks, which are not DHTs, which do not map keys to values, which just allow you to search. But if you want to build a little bit more complex applications, then you don't want to search for data. Also, if you look at your computers and your hard disk, then you don't want to search like in a Google style to find the data that you want to have. So what you want to have for higher quality applications is that you create data structures that you can efficiently access. And a DHT only offers you to access one data item by its key, or one value by its key. So this is good to have, but it is not really sufficient to create higher level applications. So we could use it on a very low level. So for file system to have one value equals one file, or one email equals one email, or in a database where one entry is a value. It is good, but we also need to structure these kind of elements. So we need to have a higher level, and typically file systems come into that. So what the DHT solves is to really mapping the keys to the values. That's very efficiently done, so we really get it. So it's very good, and we can also have this replication and data load balancing and so. But what is not solved is, for example, that you can write the data item many times, or value modification. So it's up to now really just write once. So once you store under a specific key the value, and then you read it many times. So we would like to also be able to change the content, or to update it, or to replace it. Also, a big failure, so 50% of the nodes fail. So what happens? So who keeps the overview about what is lost and what to restore? And if it's not, okay, pure DHTs like Cord and Kademlia, they do not come with replication. So we need also to consider how replication can be done more generally. Consistency, that's also a point. If we would have replication and we would have access from different points in the network, then they might reach different replication points, which is good. But if we update the data, so this is related also to the first point, if we want to update the data, then we also have to find all replication elements in order to make sure that everyone has, if they search one object, they always get the latest one and the same object. And what is sometimes also not, so what is also not supported but sometimes needed is some version management. So if you update your data, that you also want to make the old versions still available. So like in Dropbox, I don't know, if you update your data, then you still can look up the previous versions, or I don't know. So this is all not offered. So what it really only offers is to store one specific value under a specific key, and that's it. You can later read it many times, but pure Kademlia and Can and Cord do not replicate, and do not allow to access to overwrite the content later on. Also Pastry doesn't allow it, and this overwriting of previous content and structuring the entries is all not really integrated and supported. So that's where P2P file system comes in. They try to also create a kind of file organization, so to really look at the data objects as files, to offer that file storage and retrieval, and also the update of the file, and also the organization and structuring of the folder structure, for example. So what is, there are different kind of levels up to which these P2P file systems can be supported. There are some solutions only support read-only objects. Then there are some which support read-write support. And beside that, you can have a look how it is implemented. So either you have a standalone application which you have to use to access the file, Or there are also some solutions which are linked to standard file systems like network file systems, so that you can seamlessly use it. And what we want to have look at is how this different solution categories looks like. And looking at the design space, so how can we build that kind of peer-to-peer file systems? There are different options and different tasks to solve. So first of all, the question is about the placement. So where should the data be stored? How should we organize where data is stored? So one option is to have the DHTs, so that you really can say, I can identify every data object that I have by its ID, and I try to organize these IDs somewhere. The second one is to have a purely random distribution, like in unstructured overlay networks, so where you really have to search for them. Or you can have something in between, where not all of the nodes are storing, but only a few selectively chosen, which have specific capabilities, so that you say, like in some super peer environment, where you have some dedicated nodes in the network which are acting as storage points. Yes. Then there's another question about so all of these points. I think we also will get a little bit into more detail, so especially the reactive part, the replication part. But so just to get an overview. So another point that beside the location of the data is how the replication is done. So how do you make sure that there's sufficient many copies of the file in the network, so if one node goes offline, then you can restore it. The simple one is replication, so that means full replication, where you have exact copies of the same content stored several times in the network. Then there are, on the other side, erasure codes, which split the file in different parts. Yeah, okay, I started otherwise around. So I start with rateless. So okay, also there you split with the rateless codes the files in different parts, and then you and these parts you share over the network, but the codes define so where you can look up the different parts, and then you can build it again. But it's sufficient to really just get the different, like in having chunks and getting the right chunks. And erasure codes, that's a little bit extended. You have chunks. You split them around in the network, but you can also combine the chunks to restore other chunks. So in the beginning, you create, let's say, 100 chunks. Then out of these 100 chunks, you create 150 erasure code chunks. And it doesn't matter which 100 out of these 100 you get, which 100 out of these 150 erasure code chunks you get, you can still restore all other chunks. So for the second part, it's important which chunks you select. For the later one, it doesn't matter which chunks you select, you just need a sufficient number of chunks. Okay, we will also have a look at this in detail. And then there's the question of how to maintain the replications. So because this is what I just talked about, let's say the full replication. In the beginning you decide I want to have 5 replicas of the file, and then I spread it in the network. 1 day later, 2 days later, 1 week later, probably all of the nodes have gone offline. So you have to maintain the availability of the files. So to check, are still sufficient replication elements inside. And there are different approaches how you check it. There we will have some example also that's okay, I can also tell you. So there's always the proactive approach, where you actively every specific time interval you check, are all chunks there, and if not, if some is missing, then you replace it. So you actively have to periodically do this action. The other point is to reactively restore the chunks. That means you do not check whether the chunks are there or the replicas are there, but once you access some replica and it's not there, then you act. And there are different approaches. Okay, so initially you just deployed, let's say, 100 replicas, and over time you check, you use them, and then you identify one which is missing. So now you have to react. That's reactive. There are different approaches how to do it. Again, either you repair all, so everything that's missing you repair. So that one that you identified as missing, that you repair. Or you could just leave it and wait until you find even more chunks that are missing, and then you restore the identified missing ones. And the randomized, that's a little bit more complicated. There is a figure for that, so I will wait until we come to it. But what is often recommended and very useful is to have following basic techniques. If you want to create a peer-to-peer file system, there are 3 guidelines to follow. So on the one side, to split the file into blocks, that gives us more freedom and also contributes to different aspects. So first of all, load balancing. So if you have 100 megabyte file, you don't want to send it around as one piece, but you would like to split it in smaller parts, and then more peers are involved in storing it. So splitting files into blocks is good, and replicating that is anyway needed, so you need to have copies. And it's also advisable to have a list of modifications, so to know what changes are supported on the file, and to also note down which changes have been done. Okay, so if you split the files into blocks, yeah, that's the motivation. So what you want to do is to really support load balancing. So if those even big files, small files are split in equally sized blocks, we can store them on different peers. Every peer gets, over the average, the same share. Even with the biggest file, it's somehow distributed. And if some of the files have the same blocks, they can be redundantly used. This is sometimes used, so it was just observed. So if we talk about distributed data file storage, also I think many of current synchronization tools, also like Dropbox, do this. So they have a specific hash for every file or every block, and if it's already stored on their network, so first you check, is the block with this given hash already stored, and if yes, then you don't have to upload it because it's the same block. So you can really reuse this existing blocks that is shared between different files. Okay, what are the drawbacks? By spreading the blocks to different peers, of course you have more peers that share the load, and you have to make sure that, so you have to consider each of these blocks as individually to be a replicated file, so there are much more peers involved that you have to much more check for the maintaining whether there are sufficiently many replicas. Also, if you have these different blocks, you have to keep a track which blocks you have and which blocks build which file. So you have to have this meta information, metadata about which blocks belong to that file. And for this metadata, again, you have to think, how do I replicate it? Do I split this metadata in chunks or not? And if you take the blocks as too small, that would be very good for the load balancing, but you would have lots of meta information and overhead and the signaling information, who wants what. And if you have too large blocks, then otherwise you have less overhead, but more in balance. Okay, for the replication, what's the motivation? So what we do with replication, we just copy the same content to other nodes. So if the first node goes offline, there's a second copy. That's very good working. So it's good. Of course, it's just probabilistically guaranteed because if you select 5 nodes to replicate, all 5 nodes might go offline at the same time. So you don't really have a full guarantee that it's working, but it's of course probabilistic because for every node you can calculate what is the probability that he will go offline in the next 10 minutes, and even if it's 1% or so, you could calculate the overall probability that all of the nodes who have the replica go offline. So the question is much more how to coordinate these lots of replicas. So if you have these different replicas, who takes care that these replicas are always online, and if there's not enough replicas in the network, that there are new replicas created, and even you need, of course, if the network is very unreliable, then you have to increase the replica number, which typically leads to the case that only 10% of overall offered storage space of the nodes is usable, because all of the other storage space is used for replication and metadata storage. So you really have only a small amount of really usable storage space of all what the nodes offered. Okay, and the third point that was advisable is to both for the chunks and the replication, although they have some drawbacks, and so it's still required to do. So they are just a question how to solve it. And for the third part, the change logs, if you want to change stored files, and that is needed, then we have to make sure that every stored replica is modified. And also, if you want to support version control to allow really to see previous versions of the file, then it's quite useful to log which actions have been done, which modifications, to keep a log about which changes have been done. The problem here is, okay, how to know which, because the log always changes, so it's the same problem that we have here. We want to modify it. Should we have a log for the log? Should we replicate it? And then we again have the same issue. So there are different goals, different meaningful extensions to what is needed for P2P file storage, but there are also some good challenges. And if you would have some unstructured solutions, there are also some easy solutions for that. I mean, you can broadcast your changes, you can store it. It's good for small scenarios. There have been also some applications. For example, there was a tool named Groove, and later on, like it's quite frequently happening with peer-to-peer applications that become somewhat popular. So this was 2006. They are bought by Microsoft, maybe, like Skype also. And Groove was also bought by Microsoft, and now I think it's integrated into SharePoint. So what was the idea there is that you have some peer-to-peer collaboration environment where you could have a shared data folder with your friends and manage calendars and notes and so on. But it was purely unstructured, so you just flooded all the stuff that you did to the others, and that was their synchronization approach. So it was working up to 10 users, okay, because everyone was flooding what they were doing, and they were fully connected and so, but it doesn't really scale, so it's getting bigger and bigger, and you cannot keep all nodes up to date with an unstructured approach. Okay. Where I know this is okay. So the question is, so where are these peer-to-peer file real-world examples? So first of all, we don't necessarily see this at the home market. So so there are some speculations why we don't see it in our desktop PCs. One of it is that it competes with traditional file servers and the centralized solutions, and that's not supported by industry. But another view to see it is that all these peer-to-peer technologies are not taking place at the at the client devices, but more at the in the data centers. So especially if you, so I wanted to prepare, and I will prepare a nice presentation about where current peer-to-peer technologies is used, especially if we think about Amazon Cloud Share and Amazon Enterprise Solutions. They also have a set of, in their databases, in their data centers, a set of servers which are using one variant of Chord to distribute the data, the databases that they have on different machines, and to route with a Chord-like routing, which is a little bit more advanced, to the one server which is maintaining the database entry that is looked for. And also there, this file share, peer-to-peer file storage elements come in, and especially when it's about replication and replica management, then they took over quite a lot of the ideas to coordinate the many servers they have in their data centers. For real applications, so with customer devices, it's sometimes difficult to get a good enough quality. So cloud devices are very good, so cloud solutions. So how can a peer-to-peer network get as good as that? And also it's much easier to solve it centrally. So what typically is now observable, that these peer-to-peer strategies are more used in the data centers and not outside of it. Yes, I think this is more a cliffhanger, because next week we will have, so the idea was to present these modules about how the different aspects work. I think probably that we will also do this in a short time, and next week, so especially it's very interesting how the different replication aspects can be done. And so please be there to next week. That's very interesting. So once we will pick up this interesting replication schemes, and also what is very much more important is also to next week we wanted to introduce how peer-to-peer networks are currently evaluated and simulated, as this will be one of the only basically project task that is to be done, to really get familiar with it, that you can also create your mini small overlay by yourself until the end of the semester. And it's also planned in a way that it's really doable and without taking you weeks. It's just a few days. Okay, so see you then next week. And if there are any questions, then feel free to ask. Thank you.